In the last video, we have talked about utility maximization from a graphical perspective, and now we discuss the mathematical approach. To this end, we first state the problem. So we have that the consumer can buy two different goods, x1 and x2, and the utility function that describes felicity or satisfaction or whatever you would want to call it, as a function of the consumption choice of these two goods, denoted by u of x1 and x2. This function, this utility function, increases with both arguments but at a diminishing rate. What does this mean? This means that if I consume more of one good, then I increase my utility, my satisfaction or whatever, but this increase becomes smaller and smaller the higher my consumption of this good already is. Intuitively, you can think of this like you have different video games, say, and the first video game that you get brings you a lot of additional utility, right? If you have already 20 video games and you get the 21st one, then perhaps the additional utility gain that you get is not that large anymore. And in economic terms, this means that we have positive but decreasing marginal utility. You can write this down mathematically as the derivative of the utility function with respect to x1 and with respect to x2 is greater than 0. So that means utility increases if you consume more of x1 or x2. But the second derivative of the utility function with respect to x1 or x2, so the derivative of marginal utility with respect to x1 or x2, that is negative. So if your consumption is already higher, then the additional utility you get by more consumption gets smaller and smaller. And in essence, that's the same statement as if we say the utility function is concave. So it increases, but the slope decreases. The second element that we need in the problem statement is the budget constraint. And here we assume that the available budget of the consumer is M, so that's the money the consumer can spend. The price of good 1 is denoted by P1 and the price of good 2 by P2. And then it's clear that the consumer cannot spend more on X1 and X2 than the money that is available. So the price of good 1 times the amount of good 1 that is consumed plus the price of good 2 times the amount of good 2 that is consumed must be equal to the money that is available. In general, this would hold with a less than or equal sign, but in our case where the utility function has positive marginal utility, that means that we will never leave any money on the table, so we will always consume at the point where we exhaust all the available money. Then we can write down the utility maximization problem formally. So we maximize the utility function u of x1 and x2 subject to the choice of x1 and x2. So these are the two choice variables over which we maximize the utility function. And this is subject to the constraint, the budget constraint, that everything that we spend is equal to the money that we have. And then we can set up the Lagrangian function that we know from mathematical courses or from the videos that I have on static optimization. It's the utility function plus the Lagrange multiplier multiplied with the right-hand side of the constraint, where we subtract the left-hand side of the constraint from it. So that's the Lagrangian, and lambda is the Lagrange multiplier that has the interpretation of it, that it gives you the increase in utility that you would have if you relax the constraint marginally. So if I give a little bit more money, how much would the utility of the household basically change? That's a shadow price actually of the income of the household. Now we know from the method of Lagrange from mathematical courses or from the videos that I have on this topic that if you want to maximize utility, you need to find the maximum of the Lagrange function. How do you find the maximum of the Lagrange function? Well, you compute the derivative of the Lagrange function with respect to the choice variables x1 and x2 and set this equal to 0. Why is this then the maximum? Because you get to a point of the Lagrange function where the additional utility that you get by consuming more of x1 or more of x2 would be exactly balanced by the negative utility that you get for having to forego the consumption of the other good, such that you are still within your budget set, right? So at that point, the Lagrange function would be flat, and if the function is flat, that means that the derivative of the function is equal to 0. So therefore, we have the first two necessary first-order conditions for a maximum are that the derivative of the Lagrangian function with respect to the choice of good 1 must be equal to 0, and the second is that the derivative of the Lagrangian with respect to the choice of x2 must be equal to 0. Now if we look at the Lagrangian, we see the derivative with respect to x1 is the derivative of the utility function with respect to x1, and that's nothing else than marginal utility. So we have this here, marginal utility of x1. And here we have lambda multiplied by minus p1 times x1. And all the other terms do not include x1, so they drop out if we take the derivative of L with respect to x1. So we only have minus lambda times p1 left here. So this expression needs to be equal to 0. And the same argument holds true with respect to x2. So if we take the derivative of the Lagrangian, what we get is marginal utility with respect to x2. And here we get minus p2 times the Lagrange multiplier, which needs to be equal to 0. And then we have also the third necessary first-order condition, but that's a very simple one. So that's the derivative of the Lagrange function with respect to the Lagrange multiplier, and that just gives us back the constraint, right? So m minus p1 x1 minus p2 x2 must be equal to 0, and that's nothing else than the budget constraint. p1 x1 plus p2 x2 must be equal to m. So that means that we have altogether three equations in three unknowns, x1 and x2, the two choice variables, and the Lagrange multiplier, so the change in utility if the budget constraint is relaxed slightly. So what we could do in general is to solve the resulting system of the three equations for the three unknowns, and then we would get the exactly optimal choice for x1 and x2 and the associated level of the Lagrange multiplier. In our particular case here, we don't have any specification of the utility function yet, so u of x1 and x2 is not known, the functional form is not known, but we will consider a specific functional form in the next video, a specific example that is very frequently encountered. Here we derive a more general result where we just consider equations 1 and 2 from the previous slide. So 1 and 2, and we see that we can bring lambda p1 and lambda p2 to the right hand side. So then we would have the marginal utility of x1 would be equal to lambda times p1, and the marginal utility of x2 would be equal to lambda times p2. And then we divide the two expressions. In our particular case here, we don't have a specific functional form for the utility function u of x1 and x2, so it's not known yet. But we will consider a specific example in the next video where we specify a specific functional form for the utility function that we encounter very frequently in economic examples. Here we instead derive the general result when we consider the necessary first order conditions 1 and 2 from the previous slide. So if we look at that, 1 and 2, we can bring lambda times p1 to the right hand side in the first equation and lambda times p2 to the right hand side in the second equation, and we would have that the marginal utility of the consumption of good x1 must be equal to lambda times p1, and the marginal utility of the consumption of a good 2 must be equal to lambda times p2. So that's this result then here. And then we can divide these two equations. The lambda would drop out because it appears in the numerator and in the denominator on the right hand side. And we would have p1 over p2 left on the right hand side. And on the left-hand side, we would have the marginal utility of the consumption of good x1 and the marginal utility of consumption of the good 2 here, which is the ratio of the marginal utilities, and that is the marginal rate of substitution between the two goods. So we have a very intuitive result then that tells us that the ratio of the marginal utilities of the two goods must be equal to the price ratio at the optimum. What does this mean in essence? It means that how we in our preferences would be willing to substitute the two goods with one another must be equal to the ratio at which the market allows us to substitute the two goods with one another. So at this point then, we would have the situation that our indifference curve is exactly a tangent to the budget line. And we've already said that the ratio of the marginal utilities is basically the marginal rate of substitution, or more precisely the negative of the marginal rate of substitution, and that would be the price ratio P1 over P2 at the optimum. So the marginal rate of substitution would be equal to the negative price ratio. And we would again be at this point here. So we would have the slope of the indifference curve at the optimal consumption point would be equal to the slope of the budget line, which is, if we have a downward sloping curve, the negative, or if we reformulate, we would have the price ratios being the negative of the marginal rate of substitution. So this shows us that the mathematical approach leads exactly to the same result as the graphical approach. So the mathematical approach, the method of Lagrange, can be used to derive exactly the condition that we've seen graphically, that the marginal rate of substitution must be equal to the negative price ratio at the optimal choice. Now, since the intuitive interpretation is so important here, I reiterate it. At the optimum, it must hold that the ratio at which the market allows us to exchange the two goods, which is the price ratio, must be the same as the ratio that we want to substitute these two goods according to our preferences. So if we have an interior solution where we consume both goods, we would adjust consumption so long until our marginal rate of substitution is equal to the price ratio. Because exactly at this point, we cannot increase our utility anymore by consuming more of the good that we like more, right? So if at our consumption choice, we could still increase our utility, then this would be the case because we value a good more than the relative price of this good is, so that the market allows us to exchange this good for the other good in a way that we increase our utility. And if this is ruled out, then this is exactly the point at which the price ratio is equal to the marginal utility ratio, because at that point we cannot increase our utility anymore by changing our consumption choice of the two goods and still spend our whole budget. So to summarize, using the well-known method of Lagrange in terms of optimization leads us to exactly the same result that we get when we use graphical utility maximization. At the optimal consumption point, the slope of the indifference curve must be equal to the slope of the budget line, or in other words, the marginal rate of substitution must be equal to the negative price ratio of the two goods. Because at this point, we have that the market allows us to exchange the two goods exactly as our preferences would dictate it, and only at this point we cannot increase our utility anymore by changing the choice of consumption. And then the following statements are all equivalent at this point. The budget line is a tangent to the indifference curve. The ratio of the marginal utilities is the ratio of the prices, or the negative marginal rate of substitution is equal to the ratio of the prices, or the other way around, the marginal rate of substitution is equal to the negative ratio of the prices. The consumer cannot reallocate consumption within its budget and increase utility by doing that. And the rate at which the consumer is willing to substitute the two goods is equal to the rate that the market charges for substituting the two goods. So all these properties hold at the optimal choice. Thank you very much for watching the video, and I hope you found it interesting and useful. For more videos on economic content, please visit my channel that you find here to the left. And to the right, you see the next video in the series at the top, and at the bottom, you see the whole lecture in the form of a playlist.